Welcome back to the Deep Dive. This is where we take your sources, the research papers, the articles, your notes, and really dig in.
Yeah, we sift through it all to find those essential insights, the things you really need to grasp about a topic.
Exactly. We cut through the noise. And today we're tackling something absolutely vital for our energy future, solar hydrogen production.
It's a hot topic, definitely. We've got a stack of sources here covering, well, quite range different tech, economics, even where it might work best geographically.
It's complex stuff, isn't it? Sits
Yeah.
right at that intersection of solar tech, chemistry, energy strategy.
It really does.
So our mission today, using these sources, is to unpack it all. How do we make hydrogen using the sun? What are the main technologies these papers are talking about?
And where are they at? You know, what are the efficiencies, the costs, the roadblocks? Why does it all matter?
That's the plan. Ready to jump in?
Let's do it.
Okay, so let's start big picture. Why hydrogen? We hear so much about electrifying everything. Where does hydrogen fit in according to this material?
Well, what comes through really clearly is that, yeah, electrification is massive for things like cars and heating homes.
Right.
But hydrogen is positioned as, well, essential for the parts of the economy that are just really hard to decarbonize with electricity alone.
Okay, like what specifically? Do the sources give examples?
Oh, yeah. Heavy industry feedstocks are a major one. Think about making chemicals like ammonia, methanol, right now, that heavily relies on fossil fuels.
Okay, makes sense.
Steel production, too, that's another giant emitter. And these sources highlight that using green hydrogen for things like direct reduced iron, well, one paper suggests that could cut global CO2 by maybe 740 million tons a year by 2050.
Wow, 740 million tons. That's a serious number.
It really is. And then you've got long-range heavy transport.
So planes, big ships, long-haul trucks.
Exactly. The sources seem to suggest that for those sectors where batteries might be too heavy or take too long to charge, hydrogen or fuels made from hydrogen are maybe the only scalable, clean options right now.
Okay, industry transport. No less.
Energy storage, and specifically long-duration storage, seasonal storage even.
Right, so bridging those gaps when the sun isn't shining or the wind isn't blowing for, like, weeks.
Precisely. Batteries are great for hours, maybe days. But hydrogen could potentially store energy for much longer. One source mentioned a potential demand by 2050 needing like 1.2 gigatons of hydrogen just for storage.
A gigaton.
That's enormous.
It is. And another study looking at Germany's grid with lots of renewables mentioned needing maybe 17 days worth of storage capacity. Hydrogen could potentially fill that role.
So it complements electrification, filling these really specific, crucial gaps. And the focus here is very much on green hydrogen.
Absolutely. The sources are clear on this. We're
Yeah.
talking green hydrogen made using electrolysis, powered by renewables. In our case today, solar.
Which is totally different from how most hydrogen is made now. Completely different. Most of today's hydrogen is gray hydrogen. It's made from natural gas, mostly, and it actually produces a lot of CO2. One paper put the figure at about 1.1 gigatons of CO2 per year just from current hydrogen use in chemical making.
Okay, so gray is out if we're talking decarbonization. What about blue hydrogen?
Blue hydrogen is basically gray hydrogen, but they try to capture the CO2 emissions. It's better, but these sources really emphasize that electrolysis powered directly by renewables, like solar, is the only pathway they're considering that's truly fully green from start to finish.
Got it. Green hydrogen is the goal here. So how do we actually make it using solar? These sources seem to break it down into a couple of main families of methods.
Yeah, fundamentally it boils down to two big approaches. Either you use the solar energy as electricity to drive electrolysis, those are the photo-assisted methods,
Okay.
or you use the solar energy as heat, those are the thermal methods.
Let's tackle the photo-assisted ways first. The one that seems most intuitive is probably photovoltaic electrolysis, PVEC. How does that work?
Yeah, the basic idea is pretty simple. You take standard solar panels, PV panels, generate electricity,
Right.
and then you feed that electricity into an electrolyzer, which does the job of splitting water into hydrogen and oxygen. Two separate steps, basically, but connected.
And the sources mention different ways of connecting them.
They do. There's what they call traditional PVEC, where you've got your solar farm here, your electrolyzer plant there, connected by wires, standard setup.
Okay.
But then there's also integrated PVEC. The idea there is to put the PV and electrolyzer components much closer together, maybe even integrated onto the same device, to cut down on energy losses between the two.
Interesting. And this isn't brand new.
Apparently not. One source mentioned the first demo was way back in 1977 using a solar array from the Mariner 4 space probe.
Huh, that's cool. What about efficiency? How much hydrogen do you get out for the sunlight going in, the solar to hydrogen or SDH efficiency?
It's improved a lot from those early days. Traditional PDEC systems, the separate ones, can apparently reach up to 30% TH efficiency now, which is pretty good.
30%, okay.
Integrated systems are catching up too. One example mentioned achieved 19.8% CH, though that was under concentrated sunlight, which helps boost efficiency.
And what are these systems made of? Standard silicon solar panels.
Often, yes, standard silicon is used for the PV part, especially for larger scale. But to really push those efficiencies, particularly in those integrated or concentrated setups, they sometimes use more exotic, expensive materials like 3V multi-junction cells. Think high-performance stuff like for satellites.
But expensive, though.
Exactly. So a lot of research mentioned in these sources is looking at cheaper materials too, things like DSSCs or perovskite solar cells, trying to find that sweet spot of good efficiency and lower cost.
And on the other side, the electrolyzer. Does it matter which type you use with solar, since the power input will go up and down?
Ah, yes, that's a really crucial point these papers make. PEM electrolyzers, proton exchange membrane, they get highlighted quite a bit.
Why?
Because they're apparently really good at handling that variability. They can ramp up and down quickly with the solar power changes, and they can operate efficiently even when the power input is low, from 0% load right up to 100%.
Okay, that makes sense for pairing with renewables. What about other types?
Alkaline electrolyzers are mentioned as being more mature, maybe cheaper initially, but they're less flexible. They don't like changing loads as much and need a higher minimum power level to run efficiently.
Right.
And then there's solid oxide electrolyzers, SOEC. They have the potential for really high efficiencies, especially if you can feed them heat as well as electricity. But the sources indicate they're still mostly in the R&D phase, less mature.
Okay, so PVEC is solar electricity plus water splitting. What's the next photo-assisted method? Photoelectrochemical. Tech. How's that different?
PEC is kind of like trying to do both jobs, absorbing light and splitting water in one material or one integrated device.
So no separate solar panel and electrolyzer.
Essentially, yes. You have a special semiconductor material that when light hits it and it's in contact with water, it directly uses that light energy to drive the water splitting reaction on its surface. Often needs a little electrical push, an external bias voltage to work efficiently, but the core idea is direct light to hydrogen conversion.
Wow, okay, so the material itself is doing the heavy lifting.
Pretty much. It acts as both the light harvester and the catalyst. Efficiencies mentioned in the sources. Well, they're generally lower than PVEC right now, maybe up to 12% STH for some advanced tandem cells that combine PEC with a bit of PV.
12%.
Simpler structures are often below 10%. There was mention of some lab-scale wireless PEC devices hitting 13% STH, which is interesting, but still early days.
And the materials for PEC. Similar story to PV.
Kind of. Some high-efficiency research uses those expensive 3V materials again, but a big focus, definitely highlighted in these papers, is finding cheaper, more abundant materials that can do the job well enough and last long enough for large-scale use. That's a major research challenge.
Okay, PEC. Then the third photo method mentioned is photocatalysis, especially using powders. This sounds even more direct, almost like artificial photosynthesis.
It really is the closest analogy, yeah. You take a photocatalyst material, often just a powder like titanium dioxide, TiO2 is a common one they study, and you mix it into water.
Just mix it in.
Yeah, suspend it in the water, then you shine sunlight on it, and the powder particles absorb the light and directly use that energy to split the water molecules around them into hydrogen and oxygen.
Why use a powder? What's the advantage there, according to the sources?
The big advantage is surface area. Powders have a huge surface area compared to a flat film, so there's much more space for the light absorption and the chemical reaction to happen. This can mean faster reaction rates.
Okay.
Plus, making materials as powders can be cheaper than fabricating complex layered devices. They might also be easier to handle in large reactors and potentially more stable over time.
Sounds promising, potentially cheaper and simpler. Is there a catch?
The main catch is that water splitting is, as one source put it, an uphill reaction thermodynamically. It takes a lot of energy input from the light. And the big challenge is getting the hydrogen and oxygen separated efficiently and preventing them from just recombining back into water on the catalyst surface.
Wow, the back reaction.
Exactly. So you need really cleverly designed catalyst materials to push the reaction forward effectively and keep the products apart. It's complex chemistry.
Okay, so those are the main photoassisted routes, PVEC, PEC, photocatalysis. Now, let's switch gears to using solar heat. How does that work? The main one seems to be solar thermochemical water splitting.
Right. This uses concentrated solar power, think mirrors, focusing sunlight to get really high temperatures, sometimes over 1,000 degrees
Oh,
Celsius.
really hot.
Yeah.
Oh,
And you use that intense heat to drive a chemical cycle, usually involving a metal oxide material. It's typically a two-step process.
okay, walk us through this cycle. What happens?
So, step one. You heat the metal oxide material, let's say ceria is one they mention, using concentrated solar heat. At very high temperatures, it releases some of its oxygen.
Okay, it becomes reduced.
Exactly. Then, step two, you take this reduced material, cool it down a bit, and expose it to steam, to water. Because it's hungry for oxygen now, it effectively rips the oxygen atoms out of the water molecules,
Amazing.
leaving hydrogen gas, H2. The metal oxide gets oxidized again, ready for the next cycle. Materials like ZnOSO2 or iron oxides are also mentioned for these cycles.
So the metal oxide acts like a reusable chemical sponge for oxygen driven by heat.
That's a pretty good way to think about it, yeah. An advantage highlighted in the sources is that this can produce very pure hydrogen, which is good for things like fuel cells, and you're directly converting heat to chemical energy.
What about efficiency and cost here? The sources seem to give quite a range.
They did. It shows it's still an active research area. One study sounded quite optimistic, projecting maybe 44.5% energy efficiency and a cost around $1.88 per kilogram of hydrogen.
That sounds competitive.
It does. But another study cited costs closer to $7.40 per kilogram, likely with lower demonstrated efficiencies. Generally, overall efficiencies for these thermochemical systems are often below 50% currently, and the cost of the solar concentrators and the high-temperature reactors is a major challenge mentioned.
Okay. Besides splitting water directly with heat, the sources also mentioned using solar heat for solar biomass gasification and methane cracking.
Right. These use concentrated solar heat not to split water directly, but to break down other things containing hydrogen. Solar biomass gasification uses the heat to turn things like wood chips or agricultural waste into syngas, a mix of gases, including hydrogen.
Okay. And methane cracking.
That uses solar heat to break down natural gas, which is mostly methane, CH4, directly into hydrogen, H2, and solid carbon, C.
Ah, solid carbon instead of CO2. That sounds like a big environmental plus.
It definitely is. The sources point that out. You avoid the CO2 emissions and you potentially get a valuable solid carbon product like carbon black.
But there's a challenge.
Yes, managing that solid carbon. The sources mention that the carbon particles produced can gum up the works, basically. They can deactivate the catalysts used or even block the reactor flow paths. That's a key operational hurdle.
How are researchers trying to fix that?
One really interesting, though quite futuristic sounding, approach mentioned uses liquid metals.
Liquid metals.
Yeah, like heating a liquid metal up to maybe 1200 Kelvin in a special reactor. The idea is that bubbling the methane through this very hot, dense liquid metal might help the reaction happen efficiently while also helping to separate out the solid carbon particles more easily. Still early days, but innovative.
Wow, okay. That is thinking outside the box. So we've covered the main pathways using light and heat. The sources also touched on some interesting ways these systems are being combined or enhanced.
Yes, there's work on integrating different systems, like using the heat from parabolic troughs, which concentrate sunlight, to boost the efficiency of solid oxide electrolyzers, which like heat, or linking solar heat to other industrial processes like electroplating.
And the example of using waste heat from a regular solar panel seemed really practical.
That one was quite neat, yeah. A study showed you could just run a simple copper pipe with water along the back of a standard PV panel.
Okay.
The panel gets hot during operation, right? That heat, which is usually just lost, gets transferred to the water in the pipe. They showed it could heat the water quite significantly, like from 21 degrees C up to 46 degrees C.
So you get free hot water, basically.
You get useful heat, yes. But here's the kicker. By cooling the panel down slightly, by removing that heat, they also measured an increase in the panel's electricity production.
Really? How much?
The source mentioned at least a 2.5% boost in electrical efficiency. So it's a win-win. You get useful heat and slightly more electricity from the same panel. Very clever integration.
That's a great example of smart system design. Now, shifting slightly, hydrogen storage came up as a major challenge, but the sources also mentioned some new materials being explored.
Storage is definitely one of the elephants in the room for hydrogen, which we need to talk more about. But yes, research is looking beyond just compressing the gas or liquefying it. These sources highlighted experiments with materials like boron nitride, Bn, and boron carbide, Bc.
And what did they find?
They found these materials could basically soak up and store significantly more hydrogen within the same physical volume compared to just having the empty volume filled with gas.
How much more?
The numbers were pretty striking. For boron nitride, they reported storing 276% more hydrogen in the same volume. For boron carbide, it was 208% more.
Wow. That could make storage tanks much smaller or hold much more fuel.
Potentially, yes. It points towards denser, maybe more manageable physical storage. The study also noted boron nitride seemed more thermally stable, which is good for safety and practical use. Still research, but promising.
Very interesting. And to bring this back to the real-world potential, one source looked at a specific region, Canada, and estimated its solar hydrogen potential.
Right, that was a useful case study. It tried to quantify how much green hydrogen Canada could produce just from its solar resources. The estimate was over 200 million tons per year, depending on the electrolyzer tech used.
200 million tons. And did it matter where the solar panels were?
Oh, absolutely. It broke it down, showing that onshore solar potential was vastly larger, like 97% of the total, compared to offshore solar in their model.
And location within the country mattered too.
Definitely. It specifically pointed to the prairie provinces, which get the most sun, as having the highest potential. It really underscores that fundamental point. Large-scale solar hydrogen relies heavily on having good, consistent solar resources in the first place.
Okay. So we've gone from the why hydrogen's role in tackling tough emissions and storing energy through all these different hows, the photo routes, the thermal routes, these clever integrations and material advances. It's clear there's a ton of innovation happening.
Absolutely. A huge amount of scientific and engineering effort.
But like any big energy transition, the path isn't smooth. Let's dig into the main challenges that kept popping up across these sources. What are the big hurdles?
Yeah, this is crucial. It's one thing to show something works in the lab or a pilot plant, quite another to make it work economically at the massive scale needed.
And cost seems to be numero uno on the list.
It really does. High capital costs for building the plants, whether it's advanced electrolyzers, solar concentrators, high-temperature reactors, and then the operational costs.
We saw those levelized cost of hydrogen figures, the LCOH, were all over the place.
Exactly. The sources quoted numbers ranging from, what was it, maybe $6 or $7 per kilo for traditional PVEC, even higher for integrated PVEC or PEC in some studies.
Right, like $9 or even $14 per kilo.
Yeah. And then the thermochemical routes had that really optimistic $1.88 per kilo in one study, but also a more, perhaps realistic for now, $7.40 in another.
The bottom line is, for green hydrogen to truly compete with current gray hydrogen, let alone other fuels, these costs need to come down a lot.
Driven by what? Efficiency? Scale? Both. Pushing up the energy efficiency of all of these processes is key, getting more hydrogen bang for your solar buck. And then massive scale-up in manufacturing to bring down the cost of the components, plus maybe breakthroughs in cheaper materials.
Efficiency itself was mentioned as a challenge too, right? Getting those lab results into the real world.
Yes. There's often a gap between peak lab efficiency and what can be reliably achieved day in, day out in a large-scale, long-lasting industrial system. Maintaining high performance over years of operation is a big engineering challenge for many of these technologies.
And the technologies are at very different stages of readiness.
Definitely. Things like alkaline electrolysis are pretty mature, been around for ages, but many of the key green pathways we've discussed, PEM electrolysis, solid oxide, those integrated PVEC systems, PEC, the advanced thermochemical cycles, they're much earlier. Some are just entering the market, others are still firmly in R&D. They all need more development, demonstration, and significant investment to scale up.
Okay, cost, efficiency, maturity. Then there's storage. We touched on the materials, but the fundamental problems remain.
Oh yeah. The physics of hydrogen are just tricky. As a gas, it takes up a huge amount of space for the energy it carries. That's the low volumetric energy density issue.
So you need to squash it down.
Right. Either compress it to very high pressures, 700 bar tanks were mentioned for cars, that's immense pressure, or cool it down until it becomes a liquid.
which is really cold.
Extremely cold, minus 253 degrees Celsius. And getting it that cold takes a lot of energy itself. One source estimated maybe 30–40% of the energy stored in the hydrogen is used just to liquefy it.
Ouch. And liquid hydrogen doesn't just sit there.
No, you get boil off. Even in the best insulated tanks, some of it evaporates over time. The sources mentioned maybe 1–2% loss per day for vehicle tanks. Plus, there's the long-term issue of hydrogen and brittle hydrogen weakening certain metals over time, which affects tanks and pipelines.
So beyond high-pressure gas or super cold liquid, what are the storage options mentioned?
Well, chemical carriers are a big one. Converting hydrogen into something like ammonia, which is much easier to store and transport than converting it back when needed, though that conversion takes energy too.
Right.
For really large-scale storage, underground salt caverns were noted as being quite promising and technically suitable. Better than using old oil fields, apparently. And then there are those novel materials like boron nitride we discussed, trying to improve physical storage density.
And getting the hydrogen from where it's made to where it's used, another massive challenge. Transport and infrastructure.
Huge. Building dedicated hydrogen pipelines is incredibly expensive. Adapting existing natural gas pipelines is possible in some cases, but has technical challenges. Transport by truck or ship needs specialized, costly tankers. Liquid transport might be cheaper than compressed gas for really long distances, but you have the liquefaction energy cost and boil-off.
And if any non-electrolysis pathways were used, like blue hydrogen, you'd need CO2 transport and storage infrastructure too.
Exactly. That adds another whole layer of infrastructure, complexity, and cost.
What about actually using the hydrogen? Adapting our current machines?
That's another significant hurdle highlighted. End-use adaptation. Take internal combustion engines, like in trucks. They were designed for gasoline or diesel. Running them on hydrogen requires major changes.
Why? What are the issues?
Things like avoiding pre-ignition or backfire, managing potentially higher NOx emissions because hydrogen can burn hotter, and needing totally different fuel injectors and pumps. It's not a simple swap. Fuel cells are designed for hydrogen, but that means entirely new vehicle designs and refueling stations.
And finally, just getting people comfortable with it all. Public acceptance.
Yeah, the sources touch on that too. If green hydrogen costs more than gasoline or natural gas initially, that's a barrier for consumers. And just general public awareness, understanding why hydrogen is needed, how it works, that it can be handled safely, that needs building too. Policy support and education are seen as key.
Wow. Okay, we have really covered a lot of ground today, pulling all these threads from the sources. We started with why hydrogen is seen as so critical for those tough decarbonization jobs and for storing renewable energy long term. Then we explored this incredible range of ways to make it, using solar energy from straightforward PV panels powering electrolyzers to these fascinating direct light-splitting PEC and photocatalysis methods.
And using intense solar heat in those thermochemical cycles, or even for breaking down methane or biomass. Plus those clever integration ideas like capturing waste heat.
Absolutely.
Yeah.
But we also saw the stark realities of the challenges laid out in these sources, the cost hurdles, the need for better efficiency and technology scale-up, the fundamental difficulties of storing and transporting hydrogen, adapting our end-use tech.
And getting society on board. It's clear there's no single magic bullet technology here. The sources really paint a picture of a whole portfolio of different approaches being developed, each with its own pros and cons.
It's definitely a field moving incredibly fast, but the scale of the transformation needed is just immense. We've seen ideas ranging from high-tech semiconductors to simple plumbing on the back of a panel to advanced materials science for storage. It's quite the mix.
It really is.
So thinking about all that diversity and the rapid pace of development we've seen described in these sources, here's a final thought for you, the listener, to chew on. Of all the technologies we discussed today, which one that maybe seems a bit niche or less talked about right now, perhaps those powdered photocatalysts or that liquid metal methane cracking idea, or maybe something else entirely? Which one do you think might surprise us most with its potential for real, cost-effective, large-scale impact in the years ahead?
It's definitely going to be interesting to see which pathways really take off.
Indeed it will. Okay, that wraps up this deep dive. We'll be back next time digging into another set of your sources.